All right, today is day one of section 8.3. Chapter 8 basically is confidence intervals. 8.1 was the introduction to what a confidence interval is. 8.2 was confidence intervals focusing on proportions. Now it's confidence intervals focusing on means. A little bit more going on with means and proportions. It's going to take us 3 days to get through this, and we're going to need to cover quite a bit of material today to get a solid overview of everything we need to know about our t-intervals. All right, as we had discussed in previous videos, it's highly unlikely you know population standard deviation. If you knew population standard deviation, you probably wouldn't be doing the inference in the first place. Well, there need to be certain assumptions. Well, what if we know? What if we don't know? How do we handle it? So forth and so on. So here's how it plays into what we're talking about today. When a sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing. So z is kind of getting like the z-score, so to speak, for the sampling distribution. Sample mean minus the population mean divided by the whole quantity, standard deviation over the square root of the sample size. Difficulty is, we don't know this number. So, how do we handle this if we don't know this number? When we don't know sigma, we can estimate it using the sample standard deviation, S of x. So what effect does this have on the whole situation when that sigma gets replaced with that S of x? That's the deal for today. That's the deal for this entire section, basically. Okay, when we standardize based on the sample standard deviation, our statistic has a new distribution called a t-distribution. It has a different shape than the standard normal curve. Well, it's still got roughly the bell shape. That very general statement is still true, but the specifics about it are different. It is symmetric and has a single peak at 0, but has much more area in the tails. So what happens here is the normal curve for whatever these parameters or numbers turn out to be looks like this. The t-curve looks like this. So it's a little bit shorter, fatter in the middle, and it's got longer tails on each side. Like any standardized statistic, t tells us how far x bar is from the mean mu in standard deviation of units. There's a different t-distribution for each sample size specified by the degrees of freedom. Okay, here's where we get a major departure from things that have happened in the past. If you're talking about a standard normal curve, there is only one standard normal curve. For the t-distribution, it's a whole family of curves. What distinguishes the individual members of the family from each other is your degrees of freedom, which is determined by your sample size. So when we perform inference about a population mean mu using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size, making n minus 1. And by the way, df is an acceptable universal abbreviation for degrees of freedom. You're allowed to use it on the AP exam. So for the confidence intervals, working on or t confidence intervals, we're going to be doing n minus 1 degrees of freedom. And a common way you'll see that is a t little n minus 1 subscript. So, draw a simple random sample of size little n from a population as a normal distribution with mean mu and standard deviation sigma. The statistic, t equals, has a t-distribution with degrees of freedom n minus 1. When a population distribution isn't normal, this statistic will have approximately a t n minus 1 distribution if the sample size is large enough. When comparing the density curves of the normal distribution and the t-distribution, several facts are apparent. The density curves of the t-distributions are similar in shape to the normal curve. Similar in terms of they still have that basic rough bell shape to it. The spread of the t-distribution is a bit greater than a standard normal distribution, a little bit wider. The t-distributions have more probability to tails and less in the center, so it's shorter in the middle more area in the tails. As the degrees of freedom increase, the t-density curve approaches the standard normal curve ever more closely. So the higher your degrees of freedom, which means the larger your sample size, the closer the t-curve is to the z-curve. Now, in terms of where you would see this on an assessment, the most common place you would see it would be like in the multiple choice format, where it would say which of the following is true about comparing z and t curves, or which of the following is not true about comparing them, which of the following is true about t, etc., etc. So, as a free response, it's not like you're going to have to write an essay in terms of describing these things, but you need to know these facts in terms of identifying them as true or false for your typical AP type of question, AP multiple choice type of question. All right, so one of the steps in doing these problems is you are going to need a t-star, just like we needed a z-star. When we did the confidence intervals for proportions, we needed a z-star. Confidence intervals for means, when we don't know population standard deviation, we need a t-star. All right, we're going to do this two different ways. How do you do it? By working off of a table. And then how do you do it? By using technology. Now, as long as you have the choice, obviously you're going to be choosing the technology. That's pretty much always the route we go. But there are still ways that questions could be asked, they could be phrased, could be presented, that would assess your knowledge on being able to use the table. So what if we want to construct a 95% confidence interval based on a sample size of 12? Now I'm going to use a full table, which I had in front of me here, rather than a snippet of it like this, so it's easier to see. So this is your typical looking t-table that you would be provided for the AP exam when you take it. And anything that we do in here, if it's at home, clearly you'll have access to this. If you are doing it as an in-class assessment, then I would give you a copy of this. So what we have going down this way are your degrees of freedom. Going this way is your tail probability. So here we are looking at, for this problem, a 95% confidence interval. So a 95% confidence interval means it is 95% of the curve in the middle. That means that it's going to be a total of 5% between the two sides, so that's 2.5% in each tail. So 2.5%, if we're looking at the top of the table, would be right here. Also, most of these tables also have this guy on the bottom here that kind of does that mental math for you. The 95% confidence interval corresponds to 0.025% of the curve in each tail.
Pardon the interruption. At this time, will all staff please review your fire drill protocols? Again, all staff please review your fire drill protocols. The fire alarm will sound in the next few seconds. Please do not exit the building at this time. Again, the fire alarm will sound, but you do not need to exit the building. Thank you.
Sorry for that interruption. Okay, back to this. So the degrees of freedom is going to be n-1, sample size minus 1. So in this case, if our sample size is 12, our degrees of freedom is 11. We go over, that gives us a t-star of 2.201. So when we create the confidence interval in that slot where we have to put in a t-star, that's the number that would go there. This is... Alright, so wrapping up this slide, that was just a snippet.
This concludes the fire drill. Thank you.
Alright, second example of the same type, except this time it's a 95% confidence interval and a sample size of 48. Okay, so 90% confidence interval, if we're looking at the bottom, that would indicate this column here, which would correspond to 5% area in each tail. Now, if you look at the degrees of freedom, what happens with most of these tables is you reach a point where it starts skipping values. Like it gave us 1 through 30 straight through, and then it skipped to 40, 50, 60, 80, 100, 1,000. So what we have to do here with the 48 is we're always going to be more conservative. We never claim to have a sample size larger than we really do. So ideally, we'd like to have 47 degrees of freedom, but if we're working off the tables, that's not possible. What we have to do is go down to the 40. That's the biggest number that appears that's less than or equal to what we want. So that gives us a T-star of 1.684. Now, using technology, which we'll get to a little bit later in the slide, we can get a little bit better of a number to use for that. But if you're working off the table, then that would be the proper T-star to use. All right, every inference procedure that we do, right now it's confidence intervals, soon it'll be significance testing. There are always conditions that are associated with that particular inference. So if we're doing a T interval, which means that we're estimating some population mean where we don't know population standard deviation, these are the conditions we have to check. For the random condition, the data comes from well-designed random sample or randomized experiment. Okay, that's the same as it was for section 8.2. If we're sampling without replacement, we can't sample more than 10% of the population. That's the same. Okay, for the normal large sample, okay, the condition here is the population has a normal distribution or the sample size is at least 30. And this was the same thing that we had back in, back in chapter 7. That if we know that the population distribution is approximately normal, then sample size doesn't matter. Okay, if our population is unknown in terms of its shape, or it's distinctly not normal, we need to have a population of at least, a sample size rather, of at least 30. Now, if our sample size is less than 30, we can still bypass this, and we're not going to get to this today. It's either going to be tomorrow's lesson or the day after. What we have to do is check for the sample distribution. If the sample distribution does not show strong skewness or outliers, then we can still proceed. But we're going to deal with that, again, not today. We're not going to be able to get to that. Today we already have our plates full with what we need to accomplish. Okay, so when the conditions for inference are satisfied, the sampling distribution of X bar has roughly a normal distribution. Because we don't know sigma, we estimate it with the sample standard deviation S sub X. The standard error of the sample mean is the sample standard deviation divided by the square root of the sample size. To construct the confidence interval, we're going to replace the standard deviation of X bar by the standard error. Once you go from the population notation to the sample notation, we go from standard deviation to standard error. We're going to use our critical values that we just discussed with the n-1. This is the general structure of all of our confidence intervals. It's your sample statistic, which is also known as a point estimate, the critical value, which for this is a T-star, the standard deviation or the standard error of the statistic, depending on the nature of the problem, is this guy right here. So for our first example, environmentalists, government officials, and vehicle manufacturers are all interested in studying the exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides. The researchers collected data on NOx, or nitrogen oxide levels, grams per mile, for a sample of 40 light-duty engines of the same type. The mean NOx reading was 1.675, and the standard deviation was 0.3332. Construct and interpret the 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. Remember, it was emphasized, if you see these instructions, unless you're told otherwise, it's the 4-step plan. You're going to have to go through that same skeletal structure we went through with the 8.2 confidence intervals that we constructed. So, you need to start off. What are you trying to accomplish? If you're constructing a confidence interval, you're estimating a population mean. So, stating that in context for this problem, we want to estimate the true mean amount, mu, of NOx emitted by all light-duty engines of this type at a 95% confidence level. Okay, did they state the confidence level? I don't recall reading that in here. Yes, they did. They almost always do. I just didn't recall reading it. 95 is one of the more common ones, but it doesn't necessarily have to be 95. Okay, when you make this statement, make sure you're referring to the population that you're trying to estimate. We're not getting a confidence interval for that one sample of engines. There is no confidence interval if we have everything in that one sample. What we're trying to do is make a statement about all engines of that type. Okay, next thing is, if conditions are met, we should use a one sample T interval to estimate mu. Okay, how are you going to accomplish what it is you're saying you're going to estimate? The things that are important in terms of the small detail. You would like to be specific, one sample, because we're going to do two sample stuff in the near future. Is it going to be a T interval or is it going to be a Z interval? And are you estimating the mean versus the proportion? Okay, so our three conditions, the random, the 10%, large sample. Okay, the data comes from a random sample of 40 engines from the population of all light-duty engines of this type. Okay, things to be careful with here. If there is a specific descriptor in terms of what type of sample it is, make sure that you include it. For example, don't say something is a simple random sample if you don't say for sure. And then try to use wording that most closely matches the wording in the problem. Okay, we are sampling without replacement, so we need to assume that there are at least 400 light-duty engines of this type. Okay, if you know for sure that the sample is less than 10% of the total population size, then you don't have to say, and you shouldn't say, we must assume. You don't have to assume anything, you know for sure. If you don't have a number for the actual population size, then you want to include what you're assuming. Okay, for the large sample, if we knew population distribution was normal, or approximately normal, this condition gets met. Okay, they never mentioned population distribution shape, so the next thing is, as long as our sample size is at least 30, we can safely use the T distribution. Okay, if we didn't have a sample size of at least 30, and we didn't know about population distribution, you have to tune in to either tomorrow or the day after that. Okay. Now they gave us sample mean, they gave us sample standard deviation. Okay, another key thing we need to construct this interval is we need a T-star. Now if we're doing this by working off of a table, our sample size is 40, our degrees of freedom is 39. Okay, there is no column going down here, row going across rather, for 39, so we have to go to 30. You never pretend to have a larger sample size than you actually do. This is a 95% confidence interval, so that's this column right here. Our T-star is going to be 2.042. Alright, so our X-bar, our sample mean, that was given to us in the problem, plus or minus the T-star. We just did that. Sample standard deviation was given, sample size is given, order of operations gets you to here, that's the interval. Our conclusion, we are 95% confident that the interval from blah 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 to blah blah grams per mile captures a true mean level of nitrogen oxides emitted by this type of light-duty engine. Okay, we are, whatever the percentage is, confident that the interval from. Okay, that's a generic statement that's going to start all of your confidence interval conclusions. Means, you're typically going to have a unit associated with it. That's a little bit of a variation from what we had with proportions. And then captures what's the parameter that you're estimating in the context of this problem. All right, let's talk about how to get the T-star using your calculator rather than working off of the tables. So what critical T-star value should be used in constructing a confidence interval for the population mean in each of the following settings? A 95% confidence interval based on a simple random sample of size 12, a 90% confidence interval from a random sample of 48 observations. So, can we see this in the calculator? Let me move this up so we don't have a glare. So I'm going to go to distributions, which is above the vars, and we're going to scroll down to, oh, I went right past it, I'm sorry, inverse T. Okay, when we choose inverse T, we want the area under the curve. In this case, it would be the area in the tail. So for a 95% confidence interval, it would be 0.025. Our degrees of freedom are going to be one less than our sample size, which is 11. Hit paste and then enter. And it doesn't matter whether we use a positive or a negative because it's a plus minus, same deal as it was. This is usually 3 decimal places, so negative 2.201 is what we would use. Okay, let's see how that compares to what the table would give us. So our degrees of freedom were 11, 0.025, and there's the 2.201, and again, it doesn't matter whether we take a positive or a negative because it's a plus minus in the formula anyway. Normally if it says what is the T-star, you give the positive one. It's more of a convention to state the positive when you're asked, but in terms of the formula, it could be either one. All right, second part, a 90% confidence interval from a random sample of 48 observations. Slide that up so there's no glare. So second, vars to get the distributions, inverse T. This is 90% confidence interval, so it's 5% in each tail. Degrees of freedom will be 47. Paste. And we get, let me write this down on the side here, negative 1.678. We go 3 decimal places, and normally you state the positive one. So I'll put the positive one there. Now, if we were to get that number off the table, this was a 90% confidence interval, so we're in this column right here. 47 degrees of freedom we do not have. We'd have to go down to 40, and that would give us 1.684. So you see that we get a number that's slightly different than what we got working off the calculator. This is actually better because it's more accurate in terms of its degrees of freedom. One of the things that you're going to need to state within that 4-step plan that we didn't talk about in the previous problem because we didn't know about it yet is you want to be specific in terms of what degrees of freedom that you're using, and are you getting values from the table or are you getting values from the calculator? Because the confidence interval is going to be slightly different depending on which you use. Now, if you're told specifically within the problem to use a T-star obtained a certain way or a particular number of degrees of freedom, then there pretty much is only one answer. It needs to be what it is. If you're not given those specific instructions, AP rubric will allow for either set of answers to be given, or either set of answers, or it's not really, either answer to be given, a better way to phrase that. As long as you don't run that parallel solution thing. If you're describing creating the confidence interval by working off your calculator, and you're giving the answer that would correspond to working off the table, then you're not going to get credit. Or if you're talking about describing the answer with the answers, these values coming from the table, and the answer is what you get on the calculator, then you're not going to get credit. You have to pick one way or the other. Which way are you doing it? Using tables or using technology? Okay. One more example, from beginning to end, without all the little explanations in the middle. Okay, for their second semester project in AP Statistics, Ann and Tori wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. They selected a random sample of 36 cookies and found the weight of each cookie in grams. The mean weight was this, standard deviation of this. They construct and interpret a 90% confidence interval for the mean weight of an Oreo cookie. It's a little small. Okay, we wish to estimate mu, the mean weight of an Oreo cookie, at a 95% confidence level. We will construct a one-sample t-interval for mu if conditions are met. Okay, random conditions, it says specifically the cookies were randomly selected. 10% condition, sample size of 36, that's obviously less than 10% of all Oreo cookies. You don't have to assume that. That would be something that, if you've ever lived in a world and had a cookie, that would be something you would know. Okay, we do not know anything about the population distribution, but our sample size is at least 30, so we're safe using a t-distribution. Okay, because of those reasons we had said above, you have to be specific in terms of your degrees of freedom. Now, this is going to be true for anything T we do in this class. If it's a free response that involves t-distributions, part of the rubric is going to require you to state your degrees of freedom. So we're doing 35 degrees of freedom here. We are going to get that T star by using this calculator command. So we're specific of where we're getting it from, as opposed to getting it from the table. Okay, creating the confidence interval, our sample mean, that came from the problem. T star, we just stated where that came from. Sample standard deviation, sample size, order of operations, this is our interval. So we're 95% confident that the interval from 11.3645 grams to 11.4197 grams captures the true mean weight of an Oreo cookie. Now, as a what if we got the T star from the table instead of working off of the calculator? Well, there is no 35 degrees of freedom on your typical table. It jumps from 30 to 40. So you'd have to go down to 30 and then use that degrees of freedom, which would make your T star 2.042 instead of 2.03, which makes this your interval. So 11.3645, 11.364. So if we went 3 decimal places, that would round up to 1. That would stay that. So tenths, hundredths, thousandths. So you'd be off by 1,000th of a gram. Now it's still pretty close in terms of an Oreo cookie. 1,000 of a gram, like what is that? Like less than a crumb? I'm not even sure how to quantify that. But in terms of stating the numbers, there are 2 different answers. If you were going to show this work but give that answer, or show this work and give that answer, that's that whole parallel solution thing, and you're not going to get full credit for that particular part of the rubric. All right, last thing I want to talk about real quick. When we were doing our Z intervals, where are these extra things? I had said that the Z stars, you would probably know those just because you've done so much work with them. I showed you how to get the Z star on a calculator if you didn't have them memorized or they were not provided. The other place where you'll typically see the Z star, what happens as your degrees of freedom get closer and closer and closer to, or get bigger and bigger and bigger, the T distribution gets closer and closer and closer to the Z distribution, or gets closer and closer and closer to the normal curve. So what happens here is they have that theoretical, what if you have infinite degrees of freedom? In other words, now you're at a normal curve. If you look at like a 95% confidence interval, that T-star that's given is 1.96. That 1.96 is the same as the Z-star. So as a reference tool, you can get your Z-stars from the bottom line of a T table, because the infinite degrees of freedom, in theory, the T is the same as the Z. So what were the other common ones we used? The 90% to 1.1645, and then the 99% to 2.576. I think those were the ones that were provided, went the wrong one there, on that one slide of the confidence intervals for proportions. All right, that will wrap it up for today, which is day 1 of 3 days of Section 8.3.